So let's continue with light energy. Having talked about sound wave, we are now looking at light wave, light energy. Light energy. What is light? Light is that source of energy that brings about the sensation of sight or of vision. All right? That's light. It is an electromagnetic source of energy. And it travels usually in a straight line. So when I point a torch here, it travels in a what? In a straight line. All right? At a speed of 3 times 10 raised to power 8 meter per second. This is the speed of light in a vacuum. All right? The speed of light in a vacuum. What are the sources of light? We have natural source of light. We have artificial source of light. Natural sources of light includes the sun, stars, and fireflies. Those are natural sources of light. Therefore, artificial sources of light, we have bulbs. We have laser. All these are artificial sources of light. All right? So let's understand what is meant by luminous and non-luminous objects. All right? A luminous object is an object that produces light on its own. Produces light on its own is the source of light. But a non-luminous object is an object that does not produce light, but it reflects light. Like this board now, for example, is a non-luminous object. Light falls on it and bounces back. It reflects light. All right? So that's that for non-luminous objects. It emits light. So example of a luminous object is like bulb produces light. Sun produces light. Then for non-luminous, white surface now. White surface. You can have a mirror, book, moon, reflector. These are non-luminous objects. Very easy. We should understand the propagation of light. As light has its speed in, it has its speed in a vacuum. It also has its speed in water too. But let's forget about that. We don't need that right here. Okay? You can also look that up in the notes. Frequency and wavelength related to sound. Okay? We can relate it by saying C, which is what the speed of light is equal to frequency times wavelength times lambda. Okay? So the speed of light is dependent on frequency and wavelength. Then the shadow is formed when light is blocked. When you block light that is coming, for example, I am not blocking light. There is a light source here in this room. Okay, so in my studio here, when I come here, I am now blocking the light source. So you are going to see the shadow casted on the board. Can you see the shadow casted on the board? So when you partially or fully block the source of light, shadow is formed. Okay, let's look at the method at which different types of shadows are formed. Okay, there's a method at which they are formed. All right. Let's say this is a light source. Let's say this is the sun. Okay, traveling in a straight line, and we have an object here. Small object, partially blocking the sun. This object is going to cast a shadow on whatever we have here. Okay? So, because this is partially blocking the sun, some light is going to pass through here, right? So, this other part will receive light. This other upper part of this object will receive light. The lower part will receive light. But here will be dark because this object is completely blocking this place. It's casting that shadow. The shadow is going to be casted here. This place that is blocked. All right? This line. All right. So this place of total darkness that we have the shadow is called umbra. While this place that is partially dark is called penumbra. All right. While the object that blocks light, that does not allow light to pass through it, is known as opaque object. Opaque. All right. We also have other forms of objects. When we talk about light, we have transparent objects. So an object can either be opaque, transparent, which means that light can pass through. For example, transparent object is like glass. Water, light can pass through. Okay, light can pass through completely. That's why you can see through a glass, because light ray can pass through. For opaque object, light can pass through. Therefore, translucent objects, some level of light ray can pass through, but it usually appears blurry. if you try to see through a translucent object, it appears blurry. For example, you have net. Okay, net is a translucent object. You have colored glasses. Okay, those glasses that might be yellow, red, and so on and so forth. The cover of most of your bulbs, okay, that is used to diffuse light. The cover of most of your LED bulb that is usually whitish in color. Okay, those are translucent objects. Let's understand eclipse. Eclipse, solar and lunar eclipse. Solar and lunar eclipse. So for solar eclipse is when the moon is partially blocking the sun. Okay, so we have sun here, we have moon here, we have earth here. Okay, earth, we have moon, we have sun. Sun is the light source, so sun throws this light like this in a straight line to the earth. Because the moon is here, a shadow is going to be casted to the earth. Remember what we explained. And this place is going to be called umbra because it's total darkness. This place is going to be called penumbra. So this part of the earth we experience what? Umbra, total darkness. So this other part of the earth we now experience what? Penumbra. Okay, that's a partial darkness. All right. So that's that for that. They will look at lunar eclipse whereby the earth casts a shadow on the moon. You know that this moon is an opaque object, right? It's not, the moon is not opaque. Is moon opaque? Like that. Between opaque and translucent though, but it's more opaque than translucent. Let's put it as opaque. Opaque. That's why it's able to cast a shadow here. They will look at lunar, this is solar eclipse. We look at lunar eclipse. Anywhere you hear solar, just know it's related to sun. Anywhere you hear lunar, know it's related to moon. Lunar eclipse is like this. We have the moon here, and we have the earth here. Okay, and we have the sun here. Sun, earth, moon. So it's now the turn of the what? The earth to cast a shadow on the moon. The earth casts a shadow on what? On the moon. That's it. So because the sun is here, it's, you know, the sun sends light to the earth, then the earth now forms a shadow on the moon. Okay, so that's lunar eclipse for you. Lunar eclipse. The shadow is formed. Usually the light will now travel like this. You see the light travel like this and like this. All right, that's understanding solar and lunar eclipse. Pinhole camera is the foundation of camera. Okay, the pinhole camera is the foundation of camera. The foundation of anything related to camera. That's why we have to understand that pinhole camera. We can't leave it. Okay, image is formed in a pinhole camera through rectilinear propagation of light. What is rectilinear? Like this. A rectangular and linear, straight and rectangular, like this. That's the method of propagation of the light in a pinhole camera. All right, so light travels in a straight line through a small hole. All right, you have a bus, then you have a small hole in the bus, and it is through this small hole you put the object here. Through this small hole, let me just put it this side. Okay, let's put the hole here. We have the small hole here. This is the hole. Okay, so we put an object here. Then we put a light source here. Okay, this is the light source. Okay, as light falls on this object, the light that falls on the object is reflected into this small hole, moves into this small hole and fall on the screen. This is the screen of the pinhole camera. An image is formed here. The image form is usually inverted, virtual, and inverted. That's upside down. Image form in a pinhole camera. So this takes us to calculation of the magnification. Calculation of magnification. Okay. All right. Magnification M is equal to, that's the definition of magnification, image height over object height. Magnification is also equal to image distance / distance over object distance / distance. So it can be written as M is equal to image height, which is V over U. Image height is V, object height is U. Or it can be written as M is equal to image height, which is HI over HO. This can be image distance over object distance. Or it can be written as M equal to image distance, HD over object distance, HO. Alright? So don't forget this. So you can also bring the two formulas together. Magnification. You are now going to say image height, height image, height I over height O over object is equal to image distance, height D. It's not height D, it's image distance, DI, image distance over object distance, okay, DO. That's DI over DO. All right. So that's that for magnification. What is the difference between magnification and accommodation? Magnification is image height to object height. Magnification, bringing the image to the size that it is visible in whatever, whatever optics. That's magnification for you. But accommodation, there is something called accommodation and adaptation. But when we start looking at the eye and other optical instruments, we are going to talk more on that. All right. So how do you solve? It's easy. You substitute and you solve. If there is any need for conversion, you do your conversion and you solve. Reflection of light at a plane surface, like a mirror. I've taught this before in the last lesson. This is a plane surface. Let's say this is a plane mirror, for example. Now, when light ray falls on this mirror, this is the direction. It does what? It rebounds because it's a plane surface and it's reflective. It rebounds and goes to another direction. This light that falls on the mirror is known as, here is known as the normal, or the points where nothing occurs. Okay, the point of no movement. Okay, here is called the normal. Here is known as the incident light, the light that falls on the mirror. Incident light, incident ray. Here is the normal. Here is the one that is reflected after it bounces off. Reflected ray. All right, ray of light. Usually, the law of reflection states that the angle of incidence is equal to the angle of reflection. So this angle is equal to this angle. You can see that it happens at an angle. It's the same angle. Okay, angle 45, angle 45. Okay, so both angles are the same. Both these, the incident ray, the normal and the reflected ray, are all in the same plane. See, now the same plane, everything there. All right, they are all in the same plane. There's something called Snell's law, but that doesn't apply here. That applies to refraction of light. We are going to look at that very soon. Okay, we understand refraction of light where we have Snell's law. All right, there are some instruments that we have to learn here. It's commonly repeated in College of Nursing Sciences entrance exam. Instruments like periscope. Okay, application of mirror. Number one is what? Periscope. This is an instrument used to view an enclosed place that is bent. For example, you want to view through an enclosed place that is bent. Okay, you use periscope. All right, and periscope consists of what? Two mirrors at angle 45. Two mirrors at angle 45. Okay, two mirrors at an angle 45 used to view obstacles in a bent area. All right, what is angle 45? This one now, you put two mirrors like this, use it to view through obstacles because of the reflection. We have another one called kaleidoscope. This kaleidoscope is an instrument that is also used to view through an enclosed and bent region, a bent place. Use it to view through. Maybe you want to view inside my intestine now. You can put it inside to view, but just that the image form will not be as, as robust, as quality as the image form when you use fiber optic. All right, so fiber optic is the best of its kind. Okay, fiber optic is the best of its kind. All right, of optic instruments used to view internal structures where you have bent structures. Okay, so kaleidoscope produces multiple reflection. Okay, produces what? Produces multiple reflection. Why? Because it has more mirrors in it than periscope. All right. We also have sextant used for navigation, but let's forget about that one. Just know periscope and kaleidoscope. Those are the most commonly repeated. All right. We are looking at the image formed on a concave and convex mirror. All right. When talking about mirror, we have to understand the difference between concave and convex, because in a mirror, is different from lens. Mirror is different from lens. Okay. Mirror is different from lens. So we have concave and convex mirror. Those are the types of mirror. All right. Concave mirrors. Okay, under the mirrors we have concave. Concave mirror is usually curved at the center. Okay. Curved at the what center, or lighter at the center. So inward curvature, you are going to have something like this. So this is a concave mirror. All right. Concave mirror. This is a concave mirror. Then convex mirror. This convex mirror is usually thicker at the center, lighter at the edges. Okay, thick at the center. Okay, thick at the center, lighter at the edges. So we have something like this. You can see that it's thicker at the center, lighter at the edges. So concave usually curves inward curvature, but convex usually has what? Outer curvature. All right. So that's that for that. In mirror, concave mirror is known as converging mirror. All right. It's known as what? Converging mirror. Then convex mirror is known as what? Diverging mirror. Okay, what's the meaning of converging mirror? Bringing light rays together. Right? That's converge. Diverging is what? Spreading light rays. Okay, this is the direction. Spreading light rays. This one is converging, bringing it together. You can see. So, a converging mirror is concave. A diverging mirror is what? Convex. Never you forget that it is inverted in mirror. But in lens, a converging lens is convex lens. But a diverging lens is what? Concave lens. That's for lens. Okay? Do not forget that. So the reflection of light ray on a mirror, on concave or convex mirror, is usually happening in its own pattern. There is a pattern at which it happens. Okay? We also have another mirror called plane mirror, the one that is not curved. Before I forget, plane mirror. Plane mirror is not curved. Okay? That one is just plane mirror. We have to understand. So in a convex mirror, or let's say in a concave mirror, the reflection of light ray is usually higher at the middle of the mirror. Here, that's where the reflection is highest. So here is going to be where you get the reflection, at the middle of the mirror. Do not forget that. It's a very common, it's a high yield, in fact. So the image formed by a plane mirror is usually what? Let me get a marker. The image formed by a plane mirror is usually what? It's usually upright. That is straight. It's not inverted. It's virtual. And it's what? Same size. All right. Same size as the object. All right. Then the image formed by a concave mirror is usually real and inverted. Usually real and inverted. For a concave mirror, we have real / inverted image. It's going to be upside down. All right. Therefore, a convex mirror is always virtual, upright, and diminished. You know the meaning of diminished is smaller than the object. Here we have virtual image, we have upright image, and we have diminished image. All right, diminish means smaller in size. Upright means it's a ret. It's straight. Virtual is not real. It's virtual. This takes us to the lens formula or the mirror formula. Is also called the mirror formula or the lens formula. Okay, now the same thing there be. The only difference is the laws behind the formula. Okay, that's what you have to know. So let's just call it optics formula. Okay, so the mirror formula is 1 over f is equal to 1 over u plus or minus, let's use minus 1 over v, right? Or let's just use plus. This, what we have here is equal to focal length. What we have here, 1 over v plus 1 over u is equal to 1 over f, where v is what? Image height. U is what? Object height. F is what? Focal length. All of them are what? Inversed. All right, 1 over something, 1 over something, 1 over something. Okay, so you know that when we have something like 1 over f is equal to minus f, right? So when we have 1 over f raised to power minus 1. So we will have f raised to power minus 1 in algebra is equal to what? F, or f raised to power 1 in algebra. Okay, algebraic expression. So let's say you want to use this lens formula to solve. We are going to refraction of light straight up. Let's say you want to use this lens formula to solve now. For example, let's say v, which is image height, equal to 20, object height u equal to 10. They ask you to find focal length, for example. See the fastest way. 1 over f is equal to, we substitute into this formula, right? For u is 1 over 10 plus, therefore v is 1 over 20. This is the fastest way. Just times the 2 to get a numerator and plus the 2, depending on the sign you have here, either plus or minus. You plus and you get denominator. So we fair times 10 times 20 over 10 plus 20 plus or minus 20, depending on what you are doing. 20. So whatever you get, you divide and you get your answer. Okay, so how are you going to know if it's plus or minus you are going to put here? Depending on the type of mirror. If it's concave mirror we are working on, concave mirror is usually what? Negative, right? Negative v, that's negative object image height. Okay, negative image distance is usually negative, so that means we are going to use negative. It is now going to be 1 over f equal to negative 1 over v plus 1 over 20, 1 over u. If we do what we have to do here, minus this times this, that's what we are going to do. So we are now going to be left with minus something, minus this plus this. You understand? Plus times minus minus. So that tells you that you are going to use minus. So depending on the type of mirror that you are working on, all right? Depending on the type of mirror that you are working on. Like I said, this one is negative. In a concave mirror, concave, V is negative. In a concave mirror. So we have to understand the use of mirror. Remember when we talked about the image formed by a concave or convex mirror? They are images. Like concave mirror, for example, is used in car mirrors, okay? Because it gives what? A real image, right? The image is usually, though it's not real, it's you know, the image is not, it's virtual. It gives a virtual image, yes. But the image is upright. It's straight. And it covers a wider view. It gives you a wider field of view. All right? That's for the concave mirror. But the convex mirror will only give you a smaller field of view. Okay? The convex mirror gives you a smaller field of view. That's why you can't use the convex mirror in cars. You can't use it in cars. All right? What am I even saying? One forms a real image. Let's take this again. The concave mirror forms a real image, real and inverted. Convex, because it's diverging mirror, it forms an upright image and virtual image. So in cars, it's going to be better to use this one, convex mirror, because it's going to give you a visual and upright image. At least the image will be, the image will be upright. It's not going to be inverted. But when you use a concave mirror, you are going to get an inverted image. Then the mirror you use at home is just a plain mirror. Sometimes in some cars, you have also a plain mirror there. They use plain mirror too. But just know that the perfect fit, when you're talking about mirror, the perfect fit for cars is the convex mirror. Okay. But for lens, if you are talking about lens, the lens that gives a wider field of view, okay, and also give an upright image is the concave lens. But we are going to get to the optical instruments and we treat lens. All right. It's almost the same thing with mirror. All right. We have nothing much to do regarding lens. All right. But don't forget, plain mirror is usually what visual and upright. Concave mirror is usually what real and inverted. Convex mirror is usually visual and upright too. Don't forget that. Now let's look at Snell's law. Snell's law. Snell's law is applicable to refraction of light. Refraction of light ray. Remember how we define refraction? We talked about with. We define refraction as the bend of light when it enters into a medium of a different speed. So the Snell's law states that light will bend, that is going to refract when it passes through a medium of different speed. For example, I give you an example where I say here is air, here is water, water, air. All right. So when we put light ray here like this, immediately it passes air. Air is a less dense medium than water. So when it passes through the air, it enters water, which is a denser medium. It starts bending. Okay. It starts bending. That's what gives us. We now put it in a plane. This is not going to be the plane. We are not going to have, this is the plane, refraction plane. We're not going to have this one, incidented light. This one is what? Refracted light. All right. Incidented light, refracted light. This one is reflected light. Reflected. Okay. Then this one is the refracted light. It goes like this. It's supposed to bend like this. Okay. So this one, can you see? So when it goes into, let's say here is air. Here, this place is air. Air. From here like this is air. Then from here is water. I'm describing Snell's law to you now. So when the light comes from the air, immediately it enters the water, it starts what? Bending, which is refraction. Okay, refracted. Refracted ray of light. So when it refracts, it bends and it reflects out of the water. It comes out. That is Snell's law for you. So, the incident angle, the refracted angle, and reflected angle are all in the same plane. Yes. The incident angle and the reflected angle is usually the same, but the refracted angle is usually different from the incident and the reflected angle. Okay, don't forget that. So the light enters from here, incidented, refracts, bends, and reflects, comes out of the medium that it entered through. All right, and refractive index is given as refractive index, which is something like like this, is equal to sine I over sine R. All right, where I stands for what? Incident ray, R stands for what? Refracted ray. All right, incident ray and refracted ray. Don't forget that. We want to look at the formula for minimum deviation when we're talking about glass prism. All right, what is a prism? Prism. A prism is a reflective object. It can be glass, it can be other objects that has two parts at an angle. Okay, two parts at an angle. So a prism will have a shape like this. It must be angular. It must have two sides at an angle. That is a prism. So when talking about glass prism, it's a prism made of glass. All right, it's made of glass, and that's where we have minimum deviation. All right, there's a formula for minimum deviation where our n is equal to sine d, or let's open the bracket, sine a plus d. This one is the minimum deviation. This d is the minimum deviation over 2. Then we now come here to put over sine a over 2. Sine a over 2. So this is the formula for minimum deviation. So if they ask you to look for minimum deviation now, for example, you want to find minimum deviation. This is the minimum deviation. All you have to do is to substitute the rest. You substitute the angle, which is A. A is equal to angle over 2. You solve this one. You substitute the second angle over 2. Sine of the angle. When you do that, you get your minimum deviation. Just leave your minimum deviation there. And you substitute. When you substitute, you get your minimum deviation. All right. So this n here is like refractive index is equal to this. But this is the formula for minimum deviation. Okay. I think it's time to look at lenses. All right. So lenses is an optic instrument. Optical instrument. Optical instrument is lens. Optical instrument is lens. It's an optical instrument. What is optical instrument? Instruments that are used to view objects. Instruments that are used to what? To view objects are optical instruments. Lenses, mirror, what have you named them? They are generally called optical instruments. All right. And we have two types of lenses as an optical instrument. We have the converging, and which is the convex lens. When we discussed mirror not quite long ago, we talked about the meaning of converging. Okay, convex lens and also the concave lens. Convex lens, or this one we call it diverging lens. All right. So usually, anywhere you see converging lens, anywhere you see converging lens, just know that it has the outer part thicker and the edges lighter. Okay, the outer part is usually, it has the middle thicker and the edges lighter. So a convex lens is like this. Okay, while the concave lens has the middle lighter, or has a thin middle and thicker edges like this. Okay, this one is concave. All right. So this one is a converging lens. This one is a what? Diverging lens. Diverges lightweight. All right. And we have various types of concave and convex lens. You can have it as plano-concave, the one like this, plano-concave or plano-convex. This one is plano-convex, plano-concave, plano-convex. You can also have biconcave. This one is biconvex. You can also have biconcave. This one is biconcave. All right. The lens formula is also the mirror formula. That mirror formula that I told you about. It all depends, depending on the kind of objects. Okay. So U is equal to object height. U is negative when the object is real. When object is real, U is negative. We already have the formula for magnification. There's something called real and apparent depth. Real and apparent depth. Real and apparent depth. Let's understand that's real depth is the real depth of something. How deep something is. That is the real depth. But apparent depth is the depth that you can see, the one that you are seeing. That one is the apparent depth. For example, because of total internal reflection, you see a fish inside the water. This is the fish inside water. Okay, when you look from above, you are standing here, and you look from above into this water where you have this fish. Okay, you are going to see this fish as something that is closer up the water. Okay, because of total internal reflection, you are going to see it like it's not too The fish is not that deep in the water. Okay, it's not too deep in depth. I don't think the fish is that far from me. I can easily catch the fish. Okay, but the actual depth of the fish is not what you are seeing. So that one that you are seeing is known as apparent depth. But the real depth of the fish in the water, or the real depth, is known as what? The real depth. So this gives us a formula. N is equal to real over apparent depth. Refractive index. Refractive index in the medium. Refractive index in a medium is equal to, this is the symbol, refractive index is equal to real depth over apparent depth. That formula can save your life. That formula can save your life. It can save your life. So, going back to Snell's law, there's something very important I want to show you relating to Snell's law. The relation of Snell's law. The relation of Snell's law. Let me check if I can see that. Okay, Snell's law. We already talked about Snell's law. Now let's look at the relation of the Snell's law. Because you can be shown the formula and you are asked, please, from the options provided, pick the one that denotes Snell's law. So Snell's law is equal to N1, which is refractive. Refractive index 1 is equal to E times, refractive index 1 is what? Times sine I, which is what? Incident ray, is equal to what? N2, refractive index 2, sine refracted. All right? Don't forget this. Don't forget this. Let's move on to the next subtopic. No time. Optical instruments. I said we're going to eventually come to this part. What are optical instruments? Devices used for viewing / magnification. That's optical instruments. Devices you use for viewing and magnification. Okay, devices used for viewing and magnification. For example, we have microscope, all the scope, periscope, kaleidoscope, fiber optic, telescope. But here we've talked about this one: fiber optic, kaleidoscope, periscope. Now we are looking at microscope and telescope. All right. Microscope uses objective plus eyepiece for magnification. So microscope uses what? Equal to objective lens plus eyepiece. That's the lens. So you still have the one you call observer, where you look through to see, okay, what you are magnifying. Then we have telescope, objective lens, plus eyepiece for distance. This one we use it for magnification to make object bigger. Then for telescope, we use it to view distance. We use it to what? To view distance, equal to objective lens plus eyepiece, EP, eyepiece, for what? Distance. To view distance. All right. So here we have two types of microscope. We have light microscope, which can give you about 1000 magnification, 1000 times magnification. Then we have electron microscope, which can give you about 100,000 to 100 million, 100,000, 100k to 1m times magnification. 100k to 1 million times, depending on the version of the microscope. Then we have telescopes, like we have terrestrial telescope, We have Galilean telescope. So what are the objective lens found in terrestrial telescope? Terrestrial telescope is usually long, like this. That telescope you see that is usually long like this. They will stand it on top of something like this. Put it in a stand, on a stand like this. So this one here is the observer. It usually has an objective lens containing convex lens. Okay, 3 convex lens. That's what you have in a terrestrial telescope. Majorly convex lens. Only convex lens. Therefore, Galilean telescope, you have a convex lens and a concave lens as the 2 objective lens. Don't forget that. Okay? Don't forget that. The camera and the eyes, the human eyes, works what? Similarly. Why? Because they have similar structures. But before we look at that, let's understand, okay, let's leave that first of all. Let's talk about the similarities between the human eye and camera lenses. The similarities between human eye and camera is that the human eye has lens. Okay, camera also has lens. Okay, similarities. Human eyes has what? Lens. Camera also has lens. Okay, the human eyes have a photosensitive part. Okay, which is known as retina. Human eye, camera. The human eye lens is made up of crystalline. Camera lens made of plastic. Okay. Diaphragm is muscular. The ciliary muscle. Okay, controls the tone of the lens. Okay, but here we have diaphragm. Okay, we have retina, and here in camera we have photographic film, photo film. Which other thing again do we have? I think those are the most common. Lens power is giving us, lens power P, capital letter P, is giving us equal to 1 over F, where F there is focal length. And lens power is measured in diopters. Diopters. While frequency is measured in meters. Alright? Don't forget that. There's something called near point and far point. Near point is the closest place you can put an object that your eye is able to focus it and make a clear image. Okay, that's near point. It's usually 25 centimeters for a normal eye. Near point. Okay, 25 centimeters. The far point is infinity in a normal eye. So you can't determine how far you can see for a normal eye. You can put something 50 kilometers away. If you still look, you will see that thing. That's why you can see the sun. The sun that is in space. You can stand here and see the sun. So far point is infinity. Is at what? Infinity for a normal eye. This takes us to eye defects. Okay, where the far point and the near point have been compromised. Okay, eye defects. Let's look at that. Should we say eye defects or lens defects? Let's use lens defects because we are treating physics. Okay, let's use lens defects. So under lens defect, we have the most common one known as short-sightedness, short sight, called myopia. This one is when what? The ray of light focuses in front of the retina. Alright? This one is the eyeball. This one is where we have the lens. This one is the retina. The ray of light focuses here, in front of the retina, giving a short sight. Okay? It doesn't reach the retina completely. This is an object. This is the light entering. Alright? So what is it corrected with? It is corrected with a concave lens. So this is the eyeball. You put a concave lens here to correct it. So when the light enters, it's focused on the retina through the concave lens. This is the retina. Okay, look at the second one, long-sightedness, which is opposite of short-sightedness. Long sight, also called hyperopia or hypermetropia. Anyone? This one, you have the eyeball. Usually the eyeball is shorter. Here you have a shorter eyeball. Here you have a longer eyeball. Because the eyeball is shorter, light ray focuses at the back of the retina instead of on the retina. Okay, so this is the light ray coming from objects. It passes through the lens, focuses where? Here, back of the retina, behind the retina. So how do we correct this now? We use convex lens to correct it. So this is the eyeball. When we put a convex lens here, light ray enters and is focused on the retina. All right, it's focused on the retina. Corrected. We also have astigmatism. Astigmatism is as a result of what? Curvature of the eyeball. This one is more like, eye defects itself. The curvature of the cornea, abnormal curvature of the cornea. The curvature is too much, over curvature of the cornea. Then we have presbyopia. Okay, degeneration of what? Of the eye due to aging, right? It's corrected with when the lens degenerates due to aging, not the eye. Okay, it's corrected with bifocal lens. So you add convex lens and concave lens, something like this, to correct it. All right. We also have, okay, so those are the eye defects. Those are the eye defects. Let's look at something real quick before we continue. 1/. It says what? The angular magnification of a telescope. What is the angular magnification of a telescope? That's one of the questions I saw. Angular magnification of a telescope. Angular magnification of a telescope will be angle, because we have an angle 1/, the focal length, equal to observer objective lens plus objective lens plus eyepiece. All right. So the magnification will be given as objective over eyepiece now. Objective over eyepiece. Eyepiece. So that's the magnification. The question here is, the human eye differs from a camera in that a fixed lens, it has a fixed lens, that's the camera. B, an adjustable lens. C, no aperture. Hope you know the meaning of aperture. Aperture is opening. Okay, that's aperture. Opening. Or it can be referred to as opening, it can also be referred to as curvature. All right. The human eye differs from a camera in that the eye has a fixed lens. We are talking about what the eye has. B, adjustable lens. C, no aperture. D, no retina. The answer is B, adjustable lens. You know that the lens of a camera, that diaphragm in a camera controls the level of light that enters the camera. So the diaphragm is acting as a pupil. Pupil in human eye. The lens of the camera is usually fixed. Okay, but in the human eye, there is a muscle called ciliary muscle that controls the tone of the lens. Okay, it can either make it thicker or lighter. So now let's look at total internal reflection. I spoke about this before to some extent. Total internal reflection. TIR. Total internal reflection. Very important. Total internal reflection is the total reflection from an object. The total reflection from an object, all the reflection, the sum of all reflection from an object. That's total internal reflection now.